Okay, so far all the cells that we've been talking about, as we know, have been voltaic or galvanic cells, which means the cell potential has to be positive. It means that it is a thermodynamically favorable reaction. The opposite of those types of cells are what are called electrolytic cells, where the process of what's called electrolysis happens. So electrolysis is the process where you actually use energy, or in this case electricity, to force a non-spontaneous or a non-thermodynamically favorable reaction to occur. So in some ways it's kind of like the opposite of a voltaic or galvanic cell. Okay, it's really, really important to make sure that you know the difference between those two. Okay, in that, again, all electrolysis reactions in an electrolytic cell are not thermodynamically favorable, and you'll notice they do require some type of power source in order to function. Okay, and then so therefore the cell potential for an electrolytic cell is always negative. So E cell for an electrolytic cell is always negative, and then therefore always, obviously, delta G is going to be positive. So here you can see a diagram of an electrolytic cell down below. Again, same thing happens. So the anodes, the anions in the electrolyte solution are attracted towards the anode. They still undergo oxidation at the anode. Electrons again flow from the anode to the cathode. Everything's the same, except it just requires energy or electricity to do that. Okay. Now, the issue that oftentimes comes up with electrolytic cells is the fact that water can also be oxidized or reduced. So you can see in this top example here that shows water being reduced. See how the electrons are a product. And you can also see water being oxidized. So to determine which one's going to happen, is the water going to be reduced, or is something else going to be reduced? Or is the water going to be oxidized, or is something else going to be oxidized? You use the standard reduction potentials. Okay, so for the reduction process, remember that the more positive, just like that table we saw, the more positive the reduction potential, that's the one that's going to happen. So that's more likely to happen. So if water has the greater standard reduction potential, then water will be reduced before whatever else is. And then obviously with oxidation, the half reaction with the smaller, the either more negative or less positive value for the reduction potential is favored. Okay, so let's take a look at this. So here we can see we've got a table, and this is typical to what you're likely to see if there is an electrolysis question. So it says the compound NaI dissolves in pure water according to the equation NaI becomes Na plus and I minus. Some of the information in the table of standard reduction potentials may be useful in answering the questions that follow. So first of all, let's think about what we've got in the water. We've got some water particles, and we've got some sodium ions, and we've got some iodine ions. Okay, if you think about it, what's the only thing that the sodium ions can do? Can they lose another electron? They could, but it's already lost one. What's much more likely to happen is for that water to gain an electron to become sodium. Okay, you've also got the iodine ions in there. And again, what are they more likely to do? Again, they've already gained an electron to become I minus, so they're very likely to lose an electron or two. In this case, it's probably going to have to be 2. Okay, because it's already gained an electron, it's not going to gain another one. Okay, but now there's the water factor as well, because the water also can be oxidized or reduced. So we'll notice here, notice in this reaction right here, they show water as a product. Okay, and that kind of helps you understand, oh, wait a minute, that's not the water, that shows oxygen being reduced. And therefore, if you flip that equation around, that would be water being oxidized. Okay, so the reverse of this reaction would be, so this is a possible oxidation reaction. Okay, and then again, all the other ones are showing reductions. But remember, the iodine is more likely going to be oxidized rather than sodium. So really, in terms of oxidation, we've got those two choices. Okay, so these are our oxidation possibilities. And then these two here are the reduction possibilities. So again, then you have to ask yourself, and for part one, write the balanced oxidation half reaction that takes place. So in terms of oxidation, which of those two is more likely to be oxidized? Remember, these are the standard reduction potentials. Okay, and so what that means is it means that the top one, this one is more likely to be reduced, which means this one is more likely to be oxidized. So what is the oxidation half reaction? It's this reaction right here, just written as an oxidation. So it's going to be 2 I minuses becoming I2 plus our 2 electrons. And again, how do we know that it's these two up here that have to be oxidized? Well, first of all, we know this one because this one doesn't have water in the reactants. It's water that has to be oxidized. So we know right away this equation right here has to be one of our oxidation possibilities. And then it's just just understanding, okay, what do we have? We've got this and we've got this. Sodium's not going to lose another electron to become Na2+. Look at where sodium is on the periodic table. It can lose 1 electron. Remember when we talked about ionization energy? Sodium can lose 1 electron. But to lose that second one, that's when you're going to have that big jump in ionization energy. It's not going to do it. Okay? Now, in terms of reduction, which one is the larger cell potential? The sodium one or the water one? Sodium's a negative 2.71. That's a very, very low standard reduction potential. So therefore, which one is more easily reduced, water or sodium? That's what you have to ask yourself, and absolutely, it's water. Okay, so the reduction process is, I'm literally just copying it from up there. So this is the same one as above. I just had to flip it to write it as an oxidation, and then that one is the reduction reaction that takes place because, again, it has a greater or a less negative cell potential and is more likely to be reduced. Okay, and then which reaction takes place at the anode? Again, oxidation. And I'm not really sure how they want you to explain that other than oxidation, anode. You know, they both start with constants. You're not going to say that on the AP test. But in terms of, so the oxidation, because I would say something about oxidation represents losing electrons, and at the anode you are losing electrons. I mean, that's pretty straightforward, right? Okay, and now we have to write the overall equation that occurs. Luckily, our electrons are already even, 2 and 2, so those are going to cancel out for our overall equation. So we're going to have the reactants are 2I minus plus 2H2O, making I2 plus H2 plus 2 OH minuses. Okay, and I just combined the one from number 1 and number 2 and put them together. Okay, and then the cell potential still is the same way. It's cathode minus anode. And you want to make sure that when you do that, that it has to be a negative value. Okay, so our reduction process was this one. And iodine was the one that was oxidized, so 0.53. So we've got negative 0.83 and then minus 0.53 equals negative, I think that's negative 1.36 volts. And that would be the cell potential for that reaction. And now to calculate delta G is going to equal negative. How many electrons were transferred in this reaction? 2. So negative 2 times Faraday's constant, 96.485 kilojoules per mole volts. And our cell potential is the negative 1.36. So now the double negatives cancel each other out. So I'm just going to go 2 times 96.485 times 1.36 is going to give us a positive delta G of about 262 kilojoules per mole. Okay, so when an electrolysis reaction happens in an electrolytic cell, the cell potential will always be a negative value. And what you have to determine is is the water more likely to be reduced, or is the other substances in there likely to be reduced or oxidized. Okay, and the way that you can use this table here to figure out what's going to be oxidized and what's going to be reduced is just considering what do you have in that solution. Okay, we didn't have any iodine in that solution, but we had I-. Again, just like the water one, we kind of knew right away these were the two that were going to have to be flipped. Because again, we didn't have any O2 in there, we didn't have any hydrogens in there, and we didn't have any I2 in there. In our solution, we had water and we had iodide ions. And so that tells us right away those two are our oxidation possibilities. And we did have sodium ions and we did have water. So those equations are fine. So those, since they're again always written as reductions, we don't have to do anything to those ones. Okay, but when the water part is involved, and so sometimes you'll see a question about an electrolysis reaction where it'll say, that when this reaction happens, iodine is produced at the cathode, but no sodium is produced at the anode. Why not? And you say, well, that's because iodine is more easily oxidized than water is, but sodium isn't. Which means, again, that water is more easily reduced than sodium is. So even without any numbers, even if they don't tell you this, if they tell you that this is produced at the cathode, but no sodium or potassium or any other element is produced at the anode, why isn't it? Well, in an electrolysis reaction, you have to consider the water component. That if water will be more easily reduced or more easily oxidized, then it's the water that will be reduced or oxidized, not the sodium or the potassium or the lithium or whatever other element you have.